Hello, I'm Bo Weidema. This is the last video in a series of 10 on consequential modeling in lifecycle inventory analysis. This video is about errors in the background databases. I will be talking about the improvement needs for reducing the errors in the background databases, especially Ecoinvent, where the required consequential algorithms are available and documented and reasonably well implemented. In Ecoinvent, there is, of course, the general problems that are affecting all the different system models, like the lacking completeness of the database and the age of some of the data. But there are some issues that are specific to the consequential model, and that has something to do with the user interface that makes it very difficult to follow the modeling of negative physical flows, so reductions in demand, especially when the sign changes several times in a supply chain. Secondly, the mass balances are not implemented in a way that allows to use this functionality to identify errors in the modeling, which is a quite central issue for consequential modeling, to check the quality and completeness of your model. Furthermore, there are a number of induced errors in the modeling that still appear in Ecoinvent. We have some cases of joint production that are treated as combined and thereby implicitly using hidden physical allocation. This is, for example, happening in the forestry datasets. Manure emission is still part of the crop production instead of the animal husbandry systems that are causing the emissions. And the indirect land use is not implemented according to causal relationships. So it's mainly affecting biological raw materials, these manually introduced errors. So some caution have to be applied when using these data in the background. A more general problem in background databases is the issue of aggregation errors. When there is only one data set for one specific activity or product, only one geographical location and a global market for only one point in time. Even in the very lucky situation that this data set represents the global average, it is still not very likely that this represents the technology or location of the marginal suppliers. And also, this does not inform us of changes over time. In general, you can say that an average will be composed of mainly current technology, some recently installed modern technologies, and some old technologies that are being phased out. When time passes, what happens is that the modern will, of course, displace the old and eventually also the current, and then maybe an even more modern will appear. The modern technology is typically what we want to model. So using an average from the past is not really representing very well what we want to model. This has mainly to do with the efficiency improvement over time, where we are generally assuming that a modern technology is more efficient than the current, which is again more efficient than the old. So using an aggregated average will typically overestimate the impacts. If that happened throughout the database, then that would not be such a big problem. But the problem is that the extent of this bias will not be uniform across industries and products, because some industries are changing much faster than others. So what can we do to reduce this error? We could look in the long term, of course, for more differentiated data, simply ensuring that our databases become more complete, more up-to-date, and more disaggregated. This, of course, will only be possible in the long term. So can we, in the short term, find another solution, a kind of interim solution, until we have time enough to, or resources enough, to really get the full and up-to-date database with very detailed data? One possible idea is that we could use a correction factor for the marginal average ratio, so that we can apply that to the different industries, depending on, for example, learning curves, other information that may be available. This is just an idea, and I think it's an interesting option to pursue. But of course, it shouldn't stand in the way for actually collecting more detailed data. Version 3 of the Ecoinvent database has both a consequential version and a number of allocation versions or attributional versions. Does it matter which system model you choose? This I investigated some years ago. In the comparison of the 11,650 products of the Ecoinvent database at that point in time, 1,345 of these products were only found in the attributional model and not in the consequential. That was mainly byproducts, which are not relevant in the consequential version. Then there are 318 product activity combinations that were only found in the consequential model and not in the attributional. That was mainly conditional exchanges and treatments for wastes that are not produced. So because of the incompleteness of the Ecoinvent database, you will find sometimes a treatment activity for a waste that no activity is actually producing. So the remaining 9,987 product activity combinations, which were available in both the consequential and in the attributional version, were compared. The attributional version that I used was the one called allocation at the point of substitution, which was the only one available at that time. The comparison was made on the absolute difference relative to the smallest absolute value. The reason for that is that sometimes you would find a value on both sides of the zero to be compared. And to avoid that this would influence the result, I took the absolute value of the difference and divided that by the minimum of the two values. The overall results of this analysis showed that when looking across all 401 impact categories in Ecoinvent, 67% of the results had more than a 10% difference. 22% of the results have more than a 100% difference, and 16% of the results had more than a factor 2 difference. 5% of the results have more than an order of magnitude difference. Repeating this on the 11 total single score categories which were available, found somewhat less differences. And this is, of course, because when you're comparing at the single score level, different impact categories will even each other out. But still, we find 3% of the results have an order of magnitude difference or more, and 9% a factor 2 difference or more. The causes for these differences could be grouped in 5 groups. Marginal suppliers, very different from the average. Speciality products, multiple determining products, byproducts from treatment activities, and determining products heavily influenced by byproducts. I will now show an example of each of these 5 cases. If there is a large difference between the marginal and the average suppliers, then we will see big differences in the results between the attributional and consequential versions. The example here shows a market which is supplied by 99% from constrained suppliers and only 1% from marginal suppliers. If the impact of the marginal suppliers is much more important than the impact from the constrained suppliers, then you will see a result that is very different. The example I'm giving here is for land tenure using the recipe endpoint totals. So the points are recipe endpoint totals. And the market we're looking at is the market for land tenure of arable land. The constrained suppliers are those that have land that's already in use, while the unconstrained suppliers, the marginal suppliers, are the intensification and clear cutting, what we normally call indirect land use change. And this is also the cause for the very big difference in impacts. The land already in use have no indirect land use change impacts. In the attributional version, you simply sum the numbers here and you will find a total impact of 0.069 points. In the consequential version, you do not include the constraint suppliers. That means that 100% of the impact will come from the intensification and clear cutting. And that will give an impact of 6.9 points. So 2 orders of magnitude higher than the attributional version. Speciality products is when a constraint byproduct, a dependent byproduct, is specifically requested by an activity. In this case, for graphic paper, 100% recycled, the already fully utilized byproduct of paper waste is now demanded specifically for this production. In the attributional modeling, only the treatment activity is included, and the allocation occurs with the products of the waste providers. So here you see that the specialty production of graphic paper recycling, which has 51 points, again, this is values for the recipe endpoint given per ton of paper. Out of those 51 points from the graphic paper production, 47 points are allocated to the other outputs from the waste paper providers, and only 4 points to the recycled paper. The consequential model, in contrast, links to virgin production. That means that we will see a reduction in recycled tissue production, and the net effect of that is an impact of 111 points. Adding that to the 51 points from the graphic paper production gives us 162 points. So here we are having more than an order of magnitude difference. In the case with multiple determining products with no alternative production routes, the consequential model includes changes in consumption of the co-products. And the example that I could find in the Ecoinvent database is that of lanthanum oxide. That's a rare earth oxide, and in the attributional version, the allocation of the rare earth oxide production supplies only 0.352 kilograms of lanthanum for each kilogram of lanthanum out. In the consequential version, the rest of the lanthanum comes from a reduction in consumption from other consumers. And the additional output of rare earth oxides production is also included with 0.897 kilograms increased consumption. So the total system analyzed is simply much bigger in the consequential version. Now, you should note that this example is really outdated. In the current knowledge about rare earth oxides production, we know that there is only one determining product. So we wouldn't model these changes in consumptions in this way today. The reason I've included this anyway here is that this is simply the only example that I was able to find in the Ecoinvent database where this kind of modeling is applied from the consequential perspective. Then we have byproducts from treatment activities. Here we see the example with rape oil, that in the attributional version, only the treatment activity is included. Here, that is dominated by the transport inputs of 0.35 points, and the consequential model includes the displacement of other activities. In this case, the protein that is displaced on the market, and which is then supplied by soy instead, with 140 points per protein input. And again, the values are for the recipe endpoint in tons per rape meal, per ton of rape meal. Of course, a real comparison here would be that to protein. So we could look at the system of protein production from the rape oil mill, where we would see an impact of 107 points and 109 points to the oil in the allocated version. In the consequential version, we instead have 78 points for the rape oil. And of course, you see the difference here again is more than 10%. Then we have the situation where the determining products are heavily influenced by byproducts. Determining products produced together with byproducts that displays very polluting or very clean activities compared to the burden that is allocated away from the determining product in the attributional model. The example I will show you here is silicon tetrahydride, again using the recipe endpoint. Silicon tetrahydride is produced by hydrochloration of silicon, and that has a byproduct of 15.75 kilograms of psyllium tetrachloride per kilogram of silicon tetrahydride. Now, in the allocation, the majority of the impact of the silicon hydrochloration goes to the tetrachloride. However, this amount is not included in the calculation. As you can see, stoichiometrically, we have an input of 17.2 kilogram of silicium, and what goes into this silicon tetrahydride is only 0.5 kilogram of silicium. So a lot less than is actually going into the process. The consequential version displaces the silicon tetrachloride, giving a credit of 12 points. But the total of all the inputs to the system is 390 points. So the net effect of 1 kilogram of silicon tetrahydride is 378 points. So again, orders of magnitude higher. So the conclusion in this comparison is that we've identified 3 situations where consequential modeling is essential for providing correct decision support. First one is when the unconstrained marginal suppliers have much more or less impact than the average. Secondly is when you're analyzing the use of byproducts. And the third is when you're analyzing the use of determining products from activities with significant amounts of other co-products. So this is all documented in this report in the article in the International Journal of Life Cycle Assessment from 2017. This was the final conclusion of our 10 videos. If you're interested in more courses or deeper learning on other aspects of life cycle thinking, then you can follow the International Life Cycle Academy's website, where more courses are offered. Thank you for your attention.